Hi everyone, today we're going to continue our analysis on Stirling cycle by looking at their internal energy and enthalpy change for each process. So let's get started. As usual, we always like to list what's given and what are the assumptions. So the givens, we know that R is 287 joule kgK from part 1. Also, we know Cp is 1001 joule per kgK. So also, I'm going to start listing assumptions as well, because this is going to help us to solve for Cv. So we're going to assume it's ideal gas. This is the same assumption that we made previously. Ideal gas. Also, we're going to assume that Cv and Cp, they're constant because we don't want to deal with fifth-order polynomials in our calculation. Additionally, this is also a quasi-equilibrium process. So these are the same as part 1. Okay, now since we know that it's an ideal gas, so we can calculate our Cv from Cp and R if you remember the relationship between them. So Cv is just Cp minus R, which is 714 joule per kilogram K. So now we know everything that we need in order to solve for the internal energy and enthalpy. Let's get started with the first process, process 1 to 2. Let's first look at internal energy. Internal energy is Cv delta T, so T2 minus T1. So let's look at T2 and T1. So from this table, say this is table 1. So table 1 says state 1 and 2, the temperature, they're the same. So that means T2 minus T1 is 0. So that gives us a 0 internal energy as well. Similarly, for enthalpy, that is Cp delta T, T2 minus T1. So this is also 0. I wish all the processes are like this, right? But no. So let's take a look at 2 to 3. So 2 to 3. So internal energy, delta U, is Cv delta T. In this case, it's going to be T3 minus T2. Okay, we know Cv is 714. T3 from table 1, it is 500 minus T2, 300, K. This will give us 142,800 joule per kilogram. Let's start actually filling out this table. So the internal energy for state 2 to 3 is 142,800. And for the previous one, it's just 0, 0. I love that. So let's continue with our internal energy, our enthalpy, delta H, which is Cp T3 minus T2. So Cp is 1001, T3 500 minus T2 300. Then we have 200 joule per kilogram. So we can put this number here from state 2 to 3. All right, we're halfway there. So now let's take a look at state 3 to 4. I'm going to draw these lines. So 3 to 4, very, very similar. Internal energy is CV delta T. But be very careful with the delta T here. Since we're going from 3 to 4, it's going to be T4 minus T3. Okay? Similarly to the first process 1 to 2, T4 minus T3 is also 0. They're all 500K here. So the internal energy is 0. Same thing for the enthalpy. Enthalpy is Cp delta T, which is Cp T4 minus T3, which is also 0. Okay, the last one, guys. Which color should I use? Let's use orange. Forgot to put these numbers in here. So this is 0, and then the last process 421. Same thing. Internal energy is CV delta T. Since we're going from 4 to 1, we should use the T1 minus T4 in this case, right? The final minus initial. CV is 714 times T1, 300, minus T4, 500, which gives us negative 142,800 joule per kilogram. Be very careful with the sign here. We have a negative. Alright, very similar for our enthalpy. Delta H is Cp delta T. T1 minus T4. This is 1. So Cp is 1001 times 300 minus 500. I'm running out of space, so I'm just going to write on this side. It's negative 200,200 joule per kilogram. Okay, so I'm going to put these two values here, negative 142,800 and 200,200. Negative. Very important here. So make sure the signs are correct. And just for sanity check, if we add up all these values, the internal energy and enthalpy should all go back to 0, because this is a cycle and everything goes back to their original state. So that's it, guys. Great job. Thank you so much for watching, and let me know if you have any questions and comments. Thanks.